So once again, welcome to today's webinar from Flex Power Modules. The agenda for today looks like this. Following a short introduction to us as an organization, I'll go quickly into the different segmentation within the robotics market, and also talk a little bit about the different application areas that are found within those segments. Specifically then we'll focus on professional service robotics, and we'll talk a little bit about the market for that type of equipment, and also looking at the challenges and solutions in the robotic power designs that we've seen from customers recently. We'll finish up on a case study just to give you an example of one of the applications that we've been involved in. And then right at the end, we'll have a Q&A session where we'll be able to answer any of the questions that you've posed during the session. And just a reminder to use the little Q&A button at the bottom of your screens to send those questions in to us. So just a quick summary on Flex Power Modules for those of you that are not familiar. We celebrate actually our 5th anniversary this year of being acquired by Flex. Prior to that, we were part of Ericsson as Ericsson Power Modules. So many of you will be familiar with us from that sort of history. And due to that history, we've got a long legacy basically involved in the telecom world and the datacom world in particular. Very much sort of focusing on radio, routers, switches, etc. But more and more these days, we are expanding our portfolio into the industrial and transportation fields. And some of the products that you see here on the slide include some of the more encapsulated modules for those harsh, rugged environments found in the industrial segments. And today, basically, we'll focus on that industrial segment, and in particular on the robotics section, as you see in the image here. So taking a look at the robotics segmentation, basically this is split into two. On the left-hand side here, you see the industrial robotics marketplace. And this is where you'd find the robotics, or the robots rather, in industrial environments, in factories, helping to manufacture products. And there are multiple different segments involved. So you have the sort of traditional articulated robots that you see very much on factory floors, maybe doing welding or lifting and moving things across the floors. You have also delta robots, such as the products that will do pick and place, sort of moving things off one conveyor belt and moving it to another. And you also more and more now have these collaborative robots, also called cobots. And this is where we see real interaction between the robots on a production line and the human beings. They're no longer basically behind cages for safety reasons. They're actively working together with humans on production lines. The other section here, though, is the professional service robotics section. And this is where we'll focus our efforts today. But basically, this covers things like agriculture equipment, things like for placing seeds and for lifting crops, and also things like milking, for example. We also have inspection and maintenance equipment. We have construction and demolition, medical use. You see things like these sort of ecoskeletons being used for medical rehabilitation, and also search and rescue, etc. But the focus today for us we'll be looking at is more in the autonomous mobile robot market, so the AMRs, and that's, for example, in the cleaning environment and also in the transportation and logistics environment. So some of the applications involved in industrial, I've touched on already, includes the handling operations and machine tending. So robots basically working alongside machines. So being able to lift equipment into machines and be additional services within the manufacturing operations. We see things like welding and soldering. Dispensing is very much a key area. Things like epoxy resins, for example, being dispensed into modules, for example, and also things like glue dispensing. So where things need to be stuck together, these are laid down using robots. So an example there might be windscreens on automobiles, for example. Obviously, general processing within the factory environment, assembling and disassembling. And even in the clean room environment, this is becoming a major issue, obviously, with the semiconductor industry right now, trying to increase their production capacities globally, the robotics and automation segmentation of that will be huge in terms of being able to manufacture these semiconductors within the clean room environment. Looking at the professional service robotics, we talked about agriculture, just sort of looking at sort of, crop, laying out seeds and lifting crops, etc. Inspection and maintenance, construction and demolition, very much becoming an area of interest these days in terms of safety and trying to make sure that things are done in a safe environment and limiting risk to human beings. The search, rescue, and security area, again, a sort of big area. You see things like, in this case, the fire tending equipment. So being able to sort of head into dangerous areas without putting operators' lives at risk. Hospitality within hotels, more and more you start to see automated check-in functions, and even now you see these sort of humanoid type robots that we see more and more of. The medical field is massively growing as well in terms of being able to do remote surgery and operations. So that's very, very critical. But again, today's focus we'll look at is in the professional cleaning and transportation and logistics area. That's where we see the majority of growth and opportunities, at least at this stage in the professional service robotics marketplace. So looking at that market as a whole, so this is purely now the professional service robotics marketplace. The overall market for this is in excess of $100 billion. It's huge. But if we break it down a little bit, when we look at the automated guided vehicles and autonomous mobile robot marketplace, so the AGVs and the AMRs, in 2021, according to the reports here by the IFR World Robotics report, they shipped over 100,000 of those to the marketplace, which was 70% higher than 2020. So there's huge growth in this area. Of that, there was around $3 billion in revenue, or that created about $3 billion of revenue, of which 1.6 billion was for the AMR, the autonomous mobile robots. And that basically is a key change here because that overtook the AGVs for the first time. So moving from the less smart systems basically to the purely autonomous mobile robots really is the growth factor for us. By 2025, the forecast is for 640,000 AMRs to be shipped, and that's up from 82,000 in 2021. I should say this is 2021 numbers. So again, huge growth. And what's behind that growth basically is massive labor shortages and increased labor costs. COVID has been a particular problem in that regard, of course, but it was happening before then anyway. And as we've all been working from home for the last couple of years, we've all been ordering things online and expecting things to be delivered the next day to us, even the same day in some instances. And so that e-commerce growth is massively driving the manufacturing and third-party logistics companies to try and automate their processes. So you see massive, massive growth for us here. In terms of the potential markets, transportation and logistics is definitely the top application for service robotics. But you see here as well, the next one in line is the professional cleaning area. And that's why, in this discussion today, we'll focus on these two areas. That's not to dismiss any of the other applications, but these are the two that we'll discuss today. One interesting observation as well when we look globally is that most of the service robot suppliers across the globe are actually small to medium enterprises, and that means sort of less than 500 employees. So of course there are the major players, the ABBs and the Omrons and the Samsungs and Panasonics, etc. But there are a huge number of companies involved in this marketplace that are not your typical customer base that we might consider. There's sort of lots of startups, lots of new innovation going into this, and lots of new ideas. If you look at Europe as a particular example, you see here the sort of 1 to 10, 11 to 50, 51 to 200. There's a huge proportion of companies involved in robotics that are these very, very small companies, less than 200 people. So looking a bit more into detail of the challenges that we've seen when it comes to these service robots, basically, as you see on the right-hand side in the example here, these autonomous mobile robots, AMRs, are battery-driven, and the range of batteries used varies from 24 volts to 36 volts to 48 volts. In some instances, there's even talk of higher battery voltages being used, but typically it's maintained below the sort of 60 volt cell safety extra low voltage level, just purely for safety reasons, of course. That means there's a wide range of input voltages to cater for when it comes to the power supply. If you're trying to consider all the different applications globally, then we need to have some sort of solution that can cope with all these wide input voltage ranges. They're also fed and powered by typically quite poor quality or low quality AC/DC front end chargers that can be pretty noisy in terms of electrical noise, and quite often will be outside of specification in terms of charging voltages. So at least they can be pretty high when it comes to those float voltages, and sometimes see even higher voltages outside the typical float voltages. So again, from a power supply perspective, the power supply has to cope with that type of noise and voltage deviation. Within the robot itself, we have motors driving the wheels, etc. And they can be pretty noisy from an EMI perspective. So again, in terms of immunity to that sort of noise, we have to be mindful of that from a power supply perspective. And they can be operating in pretty harsh environments. So, typically these are operating in the same environment as human beings would be. So they're not like military type grade or very, very dirty, but they can be dust ingress, there can be humidity, water ingress, for example, as well as just shock and vibration. So, again, from a power supply perspective, we need to be able to deal with that sort of shock and vibration requirements on the whole. Typically, the design of the robot itself will take care of some of the other things there in terms of water ingress, humidity, etc. From a solution perspective, we need to offer small size, low weight, and be cost effective. The projections of the volumes of these robots is huge, as we looked on earlier slides. And so cost is going to be very, very important. But reducing the size, reducing the weight, that all helps in terms of extending the battery life of the unit, extending the runtime of the robot during the factory. And again, talking about that, it also needs to be high reliability. So the robot needs to be running as much of the time as possible. Any downtime, any maintenance, etc., is going to cost the user in terms of their return on investment. So very, very critical to have high reliability from a power supply perspective. Taking a look at one of the examples that we've seen in the industry for power architectures, this example basically on the right-hand side here shows you the robot in the main box and the different component parts of that robot. And then on the left-hand side here, you see the charging docking station, basically. And these robots obviously will have the battery packs, which will be typically lithium ion, lithium polymer, or nickel metal hydride. They're the most common technologies. And obviously they need charging. And that typically would be at the docking station where the robot, after being told by the monitoring circuitry that the batteries are running low, needs to go back and charge for the, and dock for the charging. Again, as we touched on earlier, the more common voltages are 24 and 36 volts. And that means basically that the float voltage needs to be in the range of 25 volts to around 54 volts. And that's the sort of voltage that will be coming in here into the compute boards, into the power distribution units, and any DC-DC converter that's in this phase will need to be able to cope with that wide input voltage range. In terms of the architecture on board, more often than not, what we're saying is that this wide input voltage range here is converted to a more stable, regulated intermediate bus voltage. And that intermediate bus voltage can be either 12 volts, very common, I would say, or more and more now, even 24 volts. And the reason for that is because the 24 volts can be used directly to power things like the motors, for example, and also some of the sensors. Many of the sensors these days are sort of 24 volt operating. But typically there would be a need in this area for an intermediate bus converter. Again, depending on the size of the robot itself, we've seen applications needing from around about 30 or 50 watts, ranging up to around 200 watts or so. Secondary stage then would be to take that 12 or 24 volt rail and convert that down to secondary voltages such as 12 volts, 5 volts, 3.3 volts, etc. And those are different voltages that might be needed by the different sensors, by the different electronic circuitry, encoder units, as it shows here, for example. So again, there will be need for point of load converters to do that conversion stage. They are often either discrete solutions or more and more as the complexity of the robot gets more, the more compute power is needed, the more current is needed from the point of load converter. And so the modularity of solutions such as those from flex power modules comes into play. Talking about that, let's take a look at some of the solutions for the bus voltages. The first one on the screen here is an 8th brick device. And this is a new platform which we'll touch on again later when we look at the case study. But this basically is an 18 to 60 volt input version of a PKBD, which is one of the very popular families that we have in our product range. And this outputs 12 volts at 240 watts. And we've actually made even further modifications to the undervoltage lockout of this one to manage even lower dips in the voltage supply. So while it operates at 18 volts, it can actually operate for short periods down to even lower voltages without the module turning off. So that can be quite useful in those quite noisy environments in terms of input voltage. If lower power is needed, we have the PKU 5513E, which is a 16th brick, and this is a 50 watt rated product with an input voltage of 18 to 75 volts. And then even lower power, we have the PKE 5313 PI, which is a 1 inch by 1 inch, 18 to 75 volt in 30 watt output device. Taking a look then at the non-isolated voltage point of load voltage rails, a couple of different solutions here that might be of interest. First is the PNA family, which is a relatively new device for us. And this basically has a very interesting input voltage range of 9 to 36 volts, quite unusual in the non-isolated point of load rails. And the output voltage is programmable from 0.9 to 5.5, and it delivers an output of up to 6 amps or 33 watts. Efficiencies are up to 96%, and as you can see here, this is an LGA device, land grid array package, but we can also deliver it with solder bumps basically already on those land grid arrays, so you can more easily mount that to your PCB. Next up is the PMU series, and this is a very small 7.5mm square package. It's 5.4 millimeter in height as well, which often means that it can be located on the back side of PCBs, so it frees up space on your PCBs as well, which can make solutions even smaller. And this has an input range of 4.5 to 17 volts, an output of 0.6 to 5.5, and is available in 3 different flavors: a 4 amp, a 6 amp, and an 8 amp variant. Again, an LGA mount package, and efficiencies in this case up to 94%. Finally, on the right-hand side here, we have a digital point of load this time. So again, 4.5 to 14 volt input, programmable from 0.6 to 3.3, with different variants, a 6 amp, a 12 amp, 15 amp, and an 18 amp output. And again, efficiency levels up to 96% in an LGA and a BGA, or a solder mount version actually. So it's not so much a ball grid array, but it's a solder grid array. But again, the key thing here is that this has a digital interface, which means that you can communicate with this particular module over the I2C PM bus communication, which means you can monitor things like the output voltages, the output currents, etc. And I'll touch on that in a slide further on, just to give you a bit more information about what that digital aspect brings to you. Finally, we have the motor control gate drive DC-DC converters. So again, these robots will have lots of motors moving the module, moving the robot along, and those motors will have gate drives, and those gate drives will need DC-DC converters. And typically we see requirements here for asymmetric output voltages. So if you're driving silicon carbide or gallium nitride or even IGBT type solutions, you'll need maybe a +20 and a -5, or a +15 and a -3. Maybe there are sort of plus or minus 15 and things like that as well. And so we offer this PUC-BG series, which is a 2-watt SIP7 package, delivering those voltages with a 6.2 kilovolt isolation level and ultra low isolation capacitance from input to output. So this is a key device really for those gate drive circuitries for the motor controls. Sister products there from that one is the PUC-B, which offers a 6 kV isolation and some various different singles and symmetric output voltages, so ±5, ±12, ±15. And if you look at the surface mount, or you prefer the surface mount design, then we have the PUB-M family as well, which offers again up to 2 watts, this time up to 3 kV, and single outputs of 5 and 12, and a dual ±5 volt. I mentioned the digital aspects of the BMR 461, and I threw this slide in just to basically give you a quick overview of what that means. And I touched on this monitoring capability, which is the first stage basically of engineers' interest in PM bus and digital converters. And the ability here is for you to be able to read the input and output voltage, the output current, the temperature of the module, and any alarms and fault handling interrupts that are basically coming over that I2C line. So that's really the first entry into digital power, and that's basically takes away some of the additional circuitry that you might be doing that anyway. It's quite common to be monitoring the current and voltages and temperature. You potentially could do away with some of that circuitry by using the digital topologies of the BMR 461. Taking it to the next step, you can actually adjust the output voltage setting, so you can do all sorts of configuration on the modules. You can address or set the PM bus addresses. You can set all the different protection features, over voltage, over temperature, over current. And if you've got multiple modules, you can do things like sequencing, current sharing, and synchronization, etc. Final stage here, really to the nth degree, is the full control, where you can do both configuration and simulation of the control loop. You can optimize the transient response of the modules, and even optimize the power dissipation and the efficiency based on input and output voltage, for example, through things like dynamic bus voltage and adaptive voltage scaling. If you'd like to learn more about that, then the first place I would send you to is the flexpowerdesigner.com website. And that's basically our free tool, which enables you to simulate and configure digital solutions offline, basically. So you don't need any hardware. You can go in, download that free of charge, and do your simulations immediately, basically. So it's a really powerful tool that I wanted to bring to your attention. So to finish up, we'll take a look at a case study that we've worked with a customer recently. This customer was or is manufacturing professional service robotics equipment. In this particular case, it's a robotic cleaner used on the factory floor environment. And the brief that we had from them was that the module or the DC-DC solution that they were looking for would need to operate over a 24 and 36 volt input on nominal input. Because it's a 24 volt battery and a 36 volt battery. There are two different versions of this, but they wanted one single DC-DC converter. The requirement was for in the range of 150 to 200 watts and a 12 volt output. As we mentioned earlier, the intermediate bus in this case was to be a 12 volt bus voltage. The solution that we've done here is to modify one of our standard and existing products, the PKB2213D. That's an 8th brick, 240 watt rated product. But as it stands, this was an 18 to 36 volt input. So the modification here for us was to modify that to an 18 to 60 volt input, which makes it suitable for these applications. What that means for the customer basically is that we gave them the input voltage that they need. We also, as I mentioned earlier, we optimized the undervoltage lockout here to take care of the slight voltage dips that they were seeing as well, even below 18 volts. We packed more than 200 watts into an 8th brick package for them, which meant a very, very small package. And the reliability of this device, it's basically a single PCB, open frame design. It's made available with a base plate package. And the MTBF of this is in the range of 5 to 6 million hours, just to give you a sort of a feel of where the MTBF is on these. So the customer was very, very happy with the solution that we were able to turn around very quickly. And that's really something I wanted to sort of bring to your attention, that while developing brand new products is obviously something we do all the time, we can also modify existing products. So if you see something in our product portfolio that is close to what you need in your robotics application, then please do bear us in mind, ask your local RSM or FAE to see if we can modify that solution as we did in this case. Here you see the module itself. I talked about the PCB being sort of a single PCB. You see that layout here with the main components laid onto that. It uses planar magnetics as well. So you see the inductor here and the main transformer. And in this particular case, this is shown with the base plate attached to the module, but we can also deliver this with open frame or in open frame without the base plate. That can help, again, reduce reduce the weight that's used in the design, and still deliver the power. Its derating is very, very good on this particular device. So just to summarize some of the ways that you can reach out to us, probably the most important one for you is the website. If you head to flexpowermodules.com, as you can see there, you'll see a lot of information available to you, including the different data sheets for all our products, but you'll also find our product selector, where you can put in your input, output voltages and your power levels, etc., and it will recommend products for you. So that's a very powerful place to head. We also have a large number of articles and blogs, both from ourselves here at Flex Power Modules, but also from our colleagues in Flex Corporate, where we talk about all sorts of different aspects of industrial and professional service robotics. We're available on LinkedIn. You can see all our latest updates on LinkedIn, and just recently we've also become live on Twitter. So please feel free to follow us on Twitter. And for our colleagues in the APAC region, we have presence on WeChat as well. Failing that, you can drop us a line as well on email to pm.info@flex.com, or pick up the phone and speak to your local RSM or FAE. So with that, I hope you found the presentation here of interest, and we look forward to discussing any questions that you might have.